This is CSE 213. The course title is Digital Design with HDL. And today is September 9, 2024. So we are talking about half adder and full adder. Half adder is the one where there are two inputs, maybe A and B, and it has two outputs, sum and carry. Whereas in full adder, there are three inputs, A, B and one more C in coming from somewhere else maybe, right, and two outputs, sum and carry, right. We also learn the important part that half adder can be realized as like sum is equal to A XOR B, and in case of carry out it's A and B. This is for half adder. For full adder, sum is equal to A XOR B XOR C in, whereas C out is equal to AB plus BC plus CA. We also learn the important part about the propagation delay. Do you remember what is propagation delay? What is propagation delay? What is propagation delay?
Theoretically, जो response हमें मिलता है कोई भी गेट का suppose not है तो A का not चाहिए उससे थोड़ा reality में delay हो जाता है.
Yeah, so it takes some time to propagate the logic going from input to output side. That time is known as the propagation delay. Excuse me, at the back, Rene. Other people, please. So the propagation delay are also of two types, TPHL and TPLH. One is going from high to low and one is going from low to high. So both of them might be different, right? In detail, maybe we'll study further on this only on propagation delay. It's a big topic. We are going to study that maybe on the advanced side when like maybe the last chapter. But before that, one more thing we need to learn, new word. It's actually not a new word but throughput. What is throughput? Have you heard about this word throughput? Throughput is the one which is output with respect to time. This is measured in terms of time, that your throughput is coming or the output is available at continuously in this particular time. So if your throughput is let's say 1 nanosecond, means if you are looking at the output every 1 nanosecond, you can see the correct output. If you remember what I mean for correct output, it depends on the propagation delay. So the output has to be available before you look at the output side. So that is deciding the throughput, right? So this is actually derived from that, right? So this is a 4-bit full adder. Those who don't want to study, they can leave while we are talking, right? So it's a 4-bit full adder where you might have each one of them. Do you want to study or not? If you know already these things, then please, those four people, you can leave, no problem. You 4 people, that girl, 2 girls and 2 boys, you leave the class, please. Not sorry, we are not small kid, right? I am not running the kindergarten. What's your name? Rutul. Can you take their names and roll number? Okay. They can give the surprise quiz, but there is no marks for that. Okay. Let's not talk, otherwise I have to deduct the marks for everyone, right? Okay. So there are two 4-bit numbers. When I am saying A and B, 4 bits means it is from A0, A1, A2 and A3, and B is equal to B0, B1, B2 and B3, and I want to add both of them. If I want to add both of them, means A3 is getting added with B3, A3 is getting added with B3, and thereafter A2 and B2 are added along with the whatever the carry is generated after this. So carry might be generated, right? And here there is one sum. So at the beginning you might require here only half adder, and later on each one of them requires 3 full adders, as there are some C0, C1 and C2, means carries are created and they are going to be added with these numbers, right? Yeah.
In the previous diagram,
He has used
we have initially used the C naught as a carry. So
it's coming from somewhere else.
the first one is a half adder.
If you are designing for this problem, then it's okay. But if it is like coming from somewhere else, so this is the continuous, like it might be coming from somewhere else, then you require full adder, right? Yeah.
Here we can't consider the A3 and B3 as a full adder, because if we have to consider, then we have to take carry from somewhere else, right?
Yes. Yes. So if you assume there is some carry, then it's full adder. They are using full adder because full adder block was available. That might be also the case. Sometimes we are saying that only implement everything with full adder, or sometimes all half adder blocks are available with you. So if you remember last time, we also learned that how to use half adder to realize full adder. To realize a full adder, you require 2 half adders in that case, right? So that might be the case here. Okay. So we studied about this, but the important problem is, if I want to see the complete sum over here, and let's assume that each gate has propagation delay of, let's say, 1 nanosecond, then how much time should I wait from those 4 people? What's your name? Yeah. Kunjal. So Kunjal, how much time I need to see this sum and carry coming from these 4 bits? How much time should I wait? 4 nanosecond. So how did you find out this 4 nanosecond? Look, inside half adder, we require gates like this, right? For other case, so now tell me, this side is full adder and this side is half adder. On critical path, how many gates are coming? You calculate it and find out how much time is required to have the sum and carry. Your answer was wrong. So again, try that. Right? Yeah. Okay. I don't know. I have to calculate. Is it correct? 20 or 7? So each one of them is 1 nanosecond. How did you find out 20? Look, half adder going from, A3 and B3 have been added, it takes only 1 nanosecond. Both are in parallel, right? You have to understand both are in parallel first of all, and you have to look at the critical path. Where is the critical path? The critical path is the one which is consuming the maximum, time, right? If this is the, let's assume that if it is like this, just I am drawing, okay, something like this. If it is something like this, some f function is there, then sum and f both are available after 3 nanosecond. You should not see after 2 nanosecond. 2 nanosecond sum is available, but f is not available, right? You have to wait for so many gates on critical path. So in this critical path there are 3, but in this both are in parallel, so you have to consider only and only 2 gates are there. So full adder is taking 2 nanosecond, right? This takes 1 nanosecond, this takes 2 nanosecond, this takes 2 nanosecond, this takes 2 nanosecond, and in total after 7 nanosecond you can see the output, means the throughput of this system is actually 7 nanosecond. If you are changing A and B, the minimum time you should give is 7 nanosecond, minimum time, and at least give one more nanosecond so that you can see, otherwise it will come and it will go, right? So additional 1 nanosecond I gave it. So if I have to design such system, I am going to give the input of at least 8 nanosecond, right, for the input side A, B and C, so that I can see the exact output. Otherwise, like it will corrupt the inputs, right? So this is what we studied, and this is what we also studied for half adder and full adder. Half adder is the one where there are 2 inputs and 2 outputs, whereas in full adder there are 3 inputs and 2 outputs, right? And you always have to consider that how many gates are there on critical path. This is the most important part. The whole thing, the whole processor design and all advanced thing in digital side, in digital domain, it's actually depending on this fact, right? And so the next important topic is the one where I should know all the carry. Before propagating, can I have any technique through which I can find out the carry and whether it's propagating that carry or not? Should like, can I know that in 1 nanosecond, something like that, or at the beginning itself? So that technique is known as the carry look ahead technique. There are plenty of topics are there, right? If you want to see, there is one more like topic is there, right? It's called subscalar design, and there are plenty of topics are there which are solving such problems, right? But this is the fundamental thing, carry look ahead or CLA. They are also calling it CLA adders, just to find out or to predict the carry before it's like you are going to see that. Here, to observe C0, C1 and C2, you have to wait for, let's say for C0 you have to wait for 1 nanosecond. For C2 you have to wait, C1 you have to wait for 3 nanosecond, and for C2 you have to wait for 5 nanosecond, right? It's available on different time instances. You want to have it at the beginning, or you want to know that like at the beginning itself. So for that there is a technique called carry look ahead. Now let's look at how the truth table look like only for carry. If it's a full adder, we are talking about full adder, and this is C out. So there are 8 inputs possibilities are there. So C out is here 0, 0, 0, but 1, 0, 1, 1 and 1. This is correct, right? So now let's not draw the K map every time, right? Without looking at K map, let's look at the how the input output relation will look like. It's a C out. C out should be, just observe this, these two lines, and then maybe you can observe for others also, where like, just make the observation. Here if you observe, you can see that no matter what C in is, right, it's not depending on C in. C in is not at all coming into picture, but C out is equal to A and B. Just looking into two bottom lines, can you say that, right? Why no? I'm just saying, just for these two. Others are there, others we have to make it OR, right? So A and B plus, so others I'm looking into that. So if you look at this, it gives 1 when inputs are different, right? Along with, so here you can, if the inputs are different and C in is also there, look, it depends on C in. If C in is 0, then the output is coming 0. Look at just, very good. So A is or B and C in, that's the function coming from these two red line, and from other. So I'm saying, if you starting from yellow two bottom lines, just concentrate on, so I'm starting again when you ask for. So if you look at this, it's A and B irrespective of what C in is, so it's not depending on this. But if you look at the red color, where this is 0 and 1 and 1 and 0, this function is A is or B, because I'm also looking at when it's becoming 1. I am not interested in other zeros, but it has to be multiplied with C in and not C in bar. If it is C in bar, then it's 0, right? So I have to make sure that these two entries are only possible when it's A bar and B times C in plus A B bar times C in, right? These two entries, yeah.
So here we can directly take C in, yes. Here we can directly take C in, but it is not dependent on A and B.
No, see, it's depending on A and B entry also, right? They are also changing. They are also changing.
But sir, the output in the
Look, there two things were consistent, same. Okay, you don't understand means, okay. Here, look at this, AB, C bar or AB, C. Can I write down this? Yeah, Vidhan? I can write down this, right?
yes.
If I am writing this as per Boolean algebra, AB, C plus C bar, so it's going to give me AB. It's same thing I was explaining in words, right? So you can't do that on top side. You have to incorporate A bar B also and AB bar, right? It's the same entries, but with the observation I am writing. We are writing with observation because this particular function A and B is the one which is going to tell me that the carry is generated. And whenever A or B is coming, name it as carry propagate. Okay. So you can write down C out is equal to G plus P times C in. So it's a new equation where there are no inputs are there. Look at this. There are no inputs are there right now. Just G, P and C in. And if you look at the carry generate and carry propagate at any number of carry, if I want, plus 1 is equal to Gi plus Pi Ci, right? And here you might have 3 bits of number, 4 bits of number. You have to plug and you have to find out the actual number. Let's assume that it is A1, sorry, just for easy, A3, A2, A1 and A0. B3, B2, B1 and B0. If you want to add both of them and if you want to find out the carry, yeah, any problem? Any problem? Rutul, those who are not studying at the back and just making noise, just ask them to leave. Okay. Okay. So if these two numbers have to be added, and if you want to find out the carry at the beginning itself, then carry is not only just AI, BI, but other components are also there. So for the case of carry 1, if you want to find out C1, C2 and C3, C0 is already 0, let's assume that. So if you want to find out C1, it has to work with A and B, means A0, B0 plus A0, XOR B0 and C0, right? Same way you can write down C2 is equal to A1, B1 plus A1 XOR B1 and C1, and you can write down other equations also, and at the beginning itself it should work. Now can we check that?
So, like this is how you can know all the carry beforehand. But then to get C2, I need to know C1.
Yeah.
I want to know C4. Usually we're just doing the whole calculation.
Yeah, we are doing the whole calculation, but these are available at 0 nanosecond. Understand? All these numbers A0, B0, everything is available at 0 nanosecond. You are adding them and you are getting the answer, right? You don't have to wait for another time like C1. So you don't have to wait for C2 is available before C1 if you want, right? You just plug the number here. The whole thing, keep it over here. It's happening on single go, right? A0, B0 and everything is available. Only on critical path you need to check, and this is useful for the case of 64 number of bits, 32 number of bits, then it's very useful. Maybe 4 bits the important might not be reflected, right? Okay. So how to subtract two numbers? How to subtract two numbers? We studied that, right? Using 2's complement, right? So what is the procedure? If you are subtracting A minus B, so you are taking 2's complement of this one and adding to the original number addend, right? So addend and 2's complement, you just look at the number, what is the sum? If carry is there, then no worry, no worry. If carry is equal to 0, then whatever the sum you got it, make the 2's complement of that, right? And add minus sign before that, right? So you will know that it's negative number, right? So in these two categories you can find out subtractor. Now let's understand that it's the same thing which is written over here, that we used A minus B using 2's complement, and by obtaining 1's complement and adding to 1 will give you the 2's complement. This is the technique. How to convert 1's complement? There are two ways to convert to 1's complement. Just add one NOT gate, it will give you 1's complement, right? And how to add 1? If I need to add 1, let's assume that this is a number. If I need to add 1, how to add that? Right? XOR gate. Right? XOR gate is the one which adds two numbers, right? So you can add both of them. This is A prime plus 1, right? If both are 1, then the output is 0. Both are different, then output is 1, right? So this is what we can do, and we have used it in half adder also, and we have used also in full adder as well, right? So this is one way. Another way, if I need to, add, or if I need to take complement of this one, this is 2's complement. This whole thing is 2's complement. This whole thing is 2's complement. We wanted to make it 2's complement by 1's complement plus 1. Why not? One's complement is only for this one. I was writing something else there and it was stayed there. Yeah, forum. This fine, it will give 2's complement, right? Okay. So let's assume that we do not have NOT gate. We do not have NOT gate. Can you implement with XOR gate? Through XOR also you can make the NOT gate. Can you make that? If I apply here 0, what will be the output? A only. A plus 0 is A. What about 1? A plus 1? What will the output? Why 1? Look, it depends on A. It's A naught, right? It's A naught. So this is another way to implement 1's complement, and again if you want to have 2's complement, right? You can have the 2's complement with this one. So both the solutions are for 2's complement. If you are reading somewhere 1's complement by mistake, then please ignore that, right? Right? So now let us assume that I wanted to find out. Yeah, tell me. Previous slide. Yeah. This is fine? Okay. Yeah. You just think about it. You think about it and tell me. Yeah, forum, do not ask your friends. So, how this XOR gate works? How XOR gate works? If both are 1, then output is 0, right? So if A is equal to 1, output is 0, right? But if A is equal to 0, output is 1, right? So it's A prime, right? Okay, so now I want to implement a 4-bit subtractor, right? So in that case, there are 2 ways. Either you can take it with the NOT gate or you can take it with XOR gate. Whichever you like, you can use it. Let's assume that I am using the NOT gate. And I am giving to a full adder where carry is equal to also 1. And I am adding 4 numbers. Note that this solution is only for unsigned number. If it is the negative number, then you have to add something further. So now these are the carries C1, C2, C3 and C4, and there are some 0, some 1, some 2 and some 3. Now let's assume that I want to subtract 10 with, let's say, 8, right? So I am expecting 2 as answer, right? It has to be 0, 0, 1, 0. Let's see that. It's unsigned number, right? So you should see the carry first of all with this architecture. Now let's start with, okay, so let's assume that there is a number which is 1010, but I want to subtract that with 1011. I should get the answer -1. Okay, in this case I should get the answer -1. So this is A and this is B. Let's start with this. This is what you wanted to repeat, right? So let's start from here. The agent is B and addend is A. So let's keep the number 1010, right? So A is 1010, right? Now let's not make mistake, and this is 1011. So this will become 0100. Scene is equal to already 1 as per our procedure. Now adding all these, now let's look at different, the answer. So 001 will give you 1, this is 0, 010, 1, 0, 100, 0, sorry 1, and this is 0, 1, and this is 0, right? So so you have to repeat the process. First of all, you have to make this, you have to take the 2's complement of this one. This 1, 1, 1, 1, all 1. So if let's make some logic over here. I also have not thought about it, but if this carry is 1, right? If this carry is 1, then you have to take the 2's complement of this one. So how to take the 2's complement of this one? Not and add with 1, right? So add all of them. Okay, take the invert of all of them and add with 1. Right, but this will only happen when this is equal to 1. Do you see? So if this is happening then and then, this should be 1. What should I keep it here? You just think about it. We are developing a logic, right? Do you understand this one? What we are doing here, right? Okay. Right. So if this is 1 and if this is also 1, this will become 1. If this is 0, by chance if this is 0, then what's the output? Whatever was the previous outputs, it's complemented of that one, right? So you just keep it that and you will get the answer. So this is one way to implement the subtractor, right? Now which one 0? So if it is overflowing, right? If it is 1, then there is no problem. If okay. So let's look at this procedure one more time. Okay. So that girl, green, yeah. What's your name? Huh? Aneri. So Aneri, please explain the procedure how to get the subtraction in binary with 2's complement method. Tell me. Wait, slowly. Okay, B is 2's complement of B. So agent and addend, right? So whatever the agent is there, you are going to take the 2's complement. 2's complement, how to take the 2's complement? 1's complement plus 1, right? Okay, it's equal to 1's complement plus 1. Now what? So you are adding this addend plus 2's complement of agent, then so you are going to have so many number of bits. If it is 4 bits, 4 sums will be available and additional carry will be there. Then if carry equal to 1, the life is easy, no problem, right? But still we have to make the whole circuit. But if it is 0, then what to do? If carry equal to 0, then whatever the answer you got it, take the 2's complement and add the negative sign, right? So that is what we did, and subtractor both together. Okay, if you have binary adder and subtractor together, then how to do that? So it is exactly same what we did it. Let's assume we are keeping m equal to 0. If m equal to 0, then what's going to happen over here? It's depending on B0 only, right? Whatever B0 is there. So can you identify this one is subtractor or adder? If m equal to 0, yeah, myth. So if m equal to 0, is it adder or subtractor? You just look at that and try to find out. It's an adder, right? It's adding two numbers, it's not subtractor. But if it is m equal to 1, it has to subtract, because this will become B0 prime, B1 prime, B2 prime, B3 prime, right? Now let's assume that if this is a circuit, what is the throughput of this circuit? The one who is shouting more, next to Hetvi, diagonally, yeah, I forgot your name, yellow t-shirt, yeah. So Dev, tell me the throughput of this particular circuit. You are giving the answer to Hetvi, right, already? Forget about it. Tell me the throughput. Throughput, yeah. Let's assume that each gate has propagation delay of 1 nanosecond, right? So 1 nanosecond full adder requires 2 gates, or how many gates are there on critical path? 2 gates, right? 2 gates we studied, right? So 2 nanosecond from each full adder for getting the sum 2 nanosecond, getting the carry 2 nanosecond. So find out. So this is after 2 nanosecond, this is 3 nanosecond, this is after 3 nanosecond, this is after 5 nanosecond, this is after 5 nanosecond. Note that this is available after 1 nanosecond itself, right? So this is again 5 nanosecond, 5 nanosecond, sorry. Right? Attention over here, I don't know, like people are not listening at the back, I think. Tell me, what's your question? How I reach here, but like for past 15 minutes I was doing that only, no? 10 nanosecond. Okay, first of all 9 nanosecond plus this is 1 nanosecond additional, right? From ZOR, so 10 nanosecond is coming from here. So I am saying for this circuit you have to make a budget. If you have to give the input, how many, like how much time after you should repeat it. So that is only